Have we just crossed the line between knowing other worlds exist and actually seeing one with our own technology? Because what James Webb may have captured is not just another astronomy update, but the kind of moment that changes what humans believe is possible. And before we go deeper, do this with me. Like this video if space still makes you feel small, subscribe if you want more stories that stretch your mind, and share this with one person who needs to see how wild the universe really is. For most of human history, planets beyond our solar system lived in the same place as myths. People imagined them. Writers dreamed about them. Scientists hoped for them. But nobody could point to the sky and say, there, that is a real world going around another star. Even after astronomy became a serious science, even after telescopes grew bigger and sharper, other worlds stayed hidden. Then the 1990s changed everything. Astronomers finally began confirming planets around other stars. That alone was huge. It proved our solar system was not some strange exception. It proved the galaxy was full of worlds. But even then, there was a catch. We usually were not seeing those planets directly. We were catching their fingerprints. We were watching their stars dim a little when a planet passed in front. We were measuring a tiny wobble in the star as a planet tugged on it. In other words, we were learning that those worlds existed without actually seeing the worlds themselves. That matters more than it sounds. Imagine hearing footsteps behind a locked door every night for years. You learn the size of the person. You learn how fast they move. You even learn when they stop and start, but you never see their face. That is how exoplanet science has felt for decades. Brilliant, precise, revolutionary, but still indirect. And that is why this story hits so hard. Scientists using the James Webb Space Telescope found compelling evidence for a planet around the young star TWA7, also called CE Antillae, about 111 light-years away. The object is called TWA7b. If further observations confirm it, this would be Webb's first direct image discovery of a planet, and the lightest world ever seen with this method outside our solar system. NASA and ESA describe it as a strong candidate, not a final confirmed planet yet, and that caution is important. But even with that caution, the result is stunning. Because this is not a shadow. This is not a graph. This is not a neat signal hidden in a spreadsheet. This is astronomers blocking the glare of a star, peeling away leftover light, and finding a faint source exactly where theory said a planet should be. That is a different level of reality. To feel why, you need to understand how brutally hard this is. Stars are monsters of brightness. A planet beside a star is tiny and dim by comparison. Trying to image one directly is like trying to spot a firefly hovering next to a stadium floodlight from miles away. The floodlight wins. The glare floods everything. The weak little glow you want is buried. That is why direct imaging is one of the hardest things in astronomy. It is not enough to have a powerful telescope. You also need a way to kill the star's blinding light without losing the planet. That is where Webb becomes more than just a giant mirror in space. The telescope used an instrument called MIRI, the mid-infrared instrument, along with a coronagraph. A coronagraph is basically a star blocker. It suppresses the star's light so faint nearby objects can emerge. Even then, it is not like turning off a lamp in a room. Some glare still leaks through. So the team then used advanced image processing to subtract the remaining starlight and clean the scene. Only after all of that did the faint source near TWA7 stand out. That one sentence sounds simple. It is not. It represents years of design, engineering, calibration, observation planning, data work, and scientific skepticism. Webb did not just snap a clean vacation photo of another world. It pulled a whisper out of a storm. Now let's talk about the star system itself, because this is where the story gets even better. TWA7 is young, extremely young. The star is only about 6.4 million years old. That is basically a newborn by cosmic standards. Our sun is around 4.6 billion years old. So when astronomers look at TWA7, they are not just looking at a star with a planet. They are looking at a system still close to its beginning, a place where the story of planet formation is still written all over the environment. Around TWA7 is a debris disk, a wide structure of dust and rocky material left over from the system's formation. Think of it like a cosmic construction zone after the biggest part of building is done, but with raw materials still spread across the site. Earlier ground-based observations had already shown that this disk contains 3 rings. And those rings were not smooth. They had structure. They had gaps. And in astronomy, gaps are rarely boring. A clean gap inside a dusty ring often means something is shaping it. Something is clearing a path. Something has enough gravity to carve order out of chaos. Very often, that something is a planet. For years, scientists suspected a hidden world might be sculpting the TWA7 disk. The problem was that suspicion is not sight. Theory is not a picture. Clues are not confirmation. Then Webb looked. The faint source appears about 1.5 arc seconds from the star on the sky, which works out to roughly 50 times the Earth-Sun distance. In our solar system, that would place it out beyond Neptune. And the placement is not random. It sits in a gap in one of the dust rings, right where researchers would expect a planet to be if that planet were shaping the disk's structure. The brightness, color, and location all line up with the idea of a young, cold, Saturn-mass planet interacting with the material around it. That is what makes this discovery feel almost cinematic. It is not just that scientists found a faint point of light, it is that they found it in the exact place where the hidden actor in this cosmic scene was supposed to stand. And the planet itself is fascinating. Initial analysis suggests TWA7b has a mass around 0.3 times Jupiter, about 100 Earth masses, roughly comparable to Saturn. That number matters a lot. Before this, directly imaged exoplanets tended to be much more massive. Big, bright, easier to spot worlds. TWA7b pushes that boundary downward in a serious way. According to the Nature paper and the mission releases, it is at least 10 times lighter than exoplanets directly imaged before. That is not a small improvement. That is a door opening. And here is where many people get confused, because when they hear another world, they imagine a second Earth. That is not what this is. TWA7b is almost certainly not a rocky, life-friendly planet. It is more like a young gas giant. NASA and ESA say the object could be near 320 Kelvin, around 47 degrees Celsius, which sounds warm by everyday human standards. But for a young planet observed in the infrared, what matters is that it is cold enough and faint enough to be extremely difficult to catch. That temperature and mass together tell us we are not dealing with some giant, super bright beast that was easy to find. We are dealing with a much subtler target. That is why astronomers are excited. This is not just a beautiful image story, it is a capability story. Every major scientific leap starts with a first success that looks narrow at the time. The first airplane did not carry hundreds of passengers across oceans. The first computer did not fit in your pocket. The first step is usually messy, limited, and easy for outsiders to underestimate. But the people inside the field know what it means. They know when a barrier has actually been broken. That is the energy around this result. If Webb can directly detect a candidate planet with about Saturn's mass inside a debris disk around a nearby young star, then the map of what becomes possible starts to change. Not instantly, not magically, not tomorrow morning. But the line moves. The impossible becomes the difficult. The difficult becomes the next target. And if you're still with me, hit like you're helping this video escape the gravity of the algorithm. Subscribe if you want more stories where science feels bigger than fiction. And share this with the one friend who always asks, okay, but why does this matter? Because the why it matters part is where this story really comes alive. For decades, astronomers have been finding exoplanets mostly through geometry. A planet crosses in front of its star, and the star dims. Or the planet's gravity makes the star wobble. Those methods are powerful. They have transformed our picture of the galaxy. But they also come with limits. A transit only works if the planet's orbit lines up just right from our point of view. Most planetary systems do not line up that way. Many worlds never pass neatly in front of their stars from Earth's angle, so a huge amount of the galaxy remains hard to study with transit methods alone. Direct imaging changes that conversation. If a planet is far enough from its star, bright enough in infrared, and the telescope plus the processing are good enough, you do not have to wait for a lucky alignment. You can go looking for the world itself. That is a huge shift. It means astronomy is not stuck only studying the planets that happen to cooperate with our viewing angle. It opens a route towards seeing more of what is really there. And TWA7b adds another layer on top of that. This candidate is not just sitting in empty space. It appears inside a debris disk, inside a gap, in a system where scientists already suspected a planet was sculpting the rings. If the object is verified as a planet, it would be the first time a world has been directly associated with shaping a debris disk this way. That is powerful because it connects theory to observation in a very clean way. Astronomers have long believed that planets help carve rings, gaps, and patterns into the dusty material around stars. It makes sense. Gravity pulls, orbits organize, matter responds. But believing it and directly seeing a candidate planet right where it should be are two very different things. One is a strong idea, the other is a scene in front of your eyes. This is how science gets stronger, not just by having good models, but by catching reality matching those models in detail. There's also a bonus mystery here that almost sounds too cool to be real. The team say the observation could be the first hint of a Trojan disk, a collection of dust trapped in the planet's orbit. In our solar system, Jupiter has Trojan asteroids that share its orbit in stable regions. If something similar is being seen around TWA7b, that would add a whole extra layer of importance to the result. It would mean we are not only spotting a candidate planet, we may also be seeing how material can gather and survive. in special orbital zones around it. That is one of the best parts of astronomy. You go out to answer one question, and the universe hands you 3 more. But now let's zoom out from the technical side and talk about the emotional side, because I think that is where people really feel this discovery. What is an image, really? An image is captured light. That is all. When you take a photo of a person, light leaves them, reaches your camera, and gets recorded. When you look at the moon, you are receiving light that came from a real object and entered your eye. Seeing is contact through light. So think about what that means here. The signal in this image traveled across about 111 light years of space. It crossed darkness so deep that the human mind can barely hold it. It kept moving long before anyone watching this video was alive. It kept moving before modern spaceflight existed. And after all of that time, it reached a telescope floating far from Earth, where a gold mirror and a set of unbelievably sensitive instruments caught it. That is not just data, that is connection. Human beings built a machine, sent it into space, and used it to catch ancient light from a possible planet around another star. If that does not move you a little, I do not know what will. And this is exactly why people are reacting so strongly to this story. We are not just getting smarter, we are changing the texture of our relationship with the universe. Other worlds are slowly moving from abstraction into imagery, from math into sight, from suspicion into presence. That change sounds subtle, but it is profound. Think about the difference between hearing that Mount Everest exists and standing where you can see it. Think about the difference between reading about the ocean and watching waves hit the shore. One is knowledge, the other is encounter. Both matter, but they do not hit the human brain the same way. For years, exoplanets have mostly belonged to the knowledge category. We knew, we calculated, we inferred. But direct imaging begins to shift at least some of them into the encounter category. And yes, the image itself is not some dramatic blue marble with clouds and continents. It is faint, processed, scientific. It does not look like a movie poster, but that is almost part of its power. This is not fantasy trying to impress you. This is reality barely visible at the edge of what our tools can do. It feels honest, it feels earned. That is why I think this moment will age well. Years from now, when telescopes get stronger and imaging gets cleaner, people may look back at TWA-7b the way we look back at the first rough airplane flights or the first blurry photos from early space missions. Not because it was the final form, but because it proved the direction was real. And that leads to the bigger question sitting underneath the whole story. If this is what we can do now, what happens next? Not next week, not next month, but next in the deeper sense. What happens over the next decade or two as techniques improve, as new observatories come online, as data processing gets better, as scientists learn from every success and every failure? What happens when the limit keeps moving? Because once a method works, even at the edge, science begins its most dangerous habit. It starts getting ambitious. Researchers stop asking, can this be done at all? And start asking, how far can we push it? And that is the question this image throws back at humanity. How much smaller a planet can we eventually see? How much fainter? How much closer to its star? How much more detail can we recover? How far can we move from seeing a glowing young giant to studying cooler and more subtle worlds? Those are not fantasy questions anymore. They are engineering questions. They are observation questions. They are the kind of questions scientists can build a career around. And that is thrilling, because history shows that once humans stop arguing about whether something is possible, progress can accelerate fast. Look at astronomy itself. There was a time when people argued about whether planets even existed around other stars. Then the evidence became overwhelming. After that, the conversation changed. Suddenly the field exploded. Thousands of exoplanets were found. Whole categories appeared. Hot Jupiters, super-Earths, mini-Neptunes, worlds orbiting 2 stars. Worlds so close to their suns they scream around them in days. Worlds in strange systems nobody would have predicted. Now direct imaging of lighter planets is hitting a similar threshold. Not the finish line, the threshold. And if this story has already blown your mind, tap like to tell the platform this kind of wonder still deserves attention. Subscribe so you do not miss the next leap, and share this video with someone who thinks space news is all hype until the facts hit them. Here is another reason this matters. Humility. Whenever our instruments improve, the universe gets less comfortable. Every time humans have built a better eye, reality has answered by becoming larger, stranger, and harder to center around us. Galileo saw moons around Jupiter and helped shatter the idea that everything circled Earth. Later, better telescopes revealed galaxies beyond our own. Modern instruments showed that what looked like empty darkness was crowded with structure. And now in our lifetime, Webb is showing us that nearby stars are not just pinpoints with mathematical companions. They are places, dynamic places, systems with architecture, movement, and hidden worlds, leaving marks in dust and light. That should reshape how we see ourselves. We live on one planet, around one star in one galaxy. And even in our local neighborhood, the universe is full of systems with their own histories. TWA7 is not some legendary location in science fiction. It is just one nearby young star among many. And yet, even there, the story is rich enough to include rings of debris, a likely planet, possible trapped dust in the planet's orbit, and a puzzle that demanded one of the greatest telescopes ever built. In other words, richness is normal out there. That idea matters. It means the cosmos is not empty until proven interesting. It is interesting almost everywhere we look closely enough. And TWA7b also reminds us that science moves carefully, even when headlines move fast. Notice the wording used by NASA, ESA, and the research team. They do not say the case is closed forever and beyond doubt. They say there is compelling evidence. They call TWA7b a strong candidate. They say, if confirmed, this would mark Webb's first direct image planet discovery. That caution is not weakness. It is strength. It is one of the reasons science deserves trust when it gets things right. Scientists are not supposed to fall in love with the first exciting interpretation and stop thinking. They test. They compare alternatives. They try to rule out background objects. They ask whether a galaxy in the wrong place could fool them. They ask whether a solar system object could mimic the signal. They check whether the source fits the expected brightness, color, and position. They do the boring, disciplined work that protects discovery from wishful thinking. That process matters because the claim is big. When you say you may have directly imaged a low-mass world around another star, you do not get to be casual. And the stronger the result survives that caution, the more impressive it becomes. That is also why the publication in Nature matters. It signals that the work was examined seriously. It does not make the conclusion sacred. Science is never sacred. But it does mean the result entered the conversation through one of the hardest doors to pass through. And I think that makes the human side of this even more beautiful. Somewhere, a team spent years building toward a moment. Most people will only experience as a headline on a screen. They planned observations. They trusted a telescope millions of miles away. They waited. They processed data. They argued over what they were seeing. They pushed against their own excitement. Then, slowly, a possible planet emerged from the glare. That is one of the quiet miracles of science. The final image looks simple. The path to earning it never is. And yet, the result reaches all of us. Because even if you never study astronomy, even if you never care about instrument design, even if you never read a single research paper, this discovery touches a very old human nerve. The part of us that has always looked up and asked the same question in different words. What else is out there? Not in theory, not in poetry, not in hope. Out there for real. This image does not answer that question fully, but it answers part of it with light. Yes. There are other worlds. Yes, we can begin to see them. Yes, the gap between imagination and observation is shrinking, and once that gap starts shrinking, it is hard to believe it will stop here. One day, a future telescope will almost certainly do more than detect a faint infrared point around another star. One day, we will push toward smaller planets, cooler planets, and eventually worlds that make people whisper the word habitable with a straight face. I'm not saying that day is tomorrow, it is not, but this is how roads begin, not with a destination, but with proof that forward is possible. That is why TWA7b matters so much. It is not the final prize. It is the opening signal. It is the moment a new method proves its nerve. It is the first time this specific telescope, our most powerful space observatory, appears to have found a planet by directly imaging it. That alone would put it in the history books. Add the low mass. Add the location inside the debris disk. Add the possibility that we are watching a planet shape its surroundings. Add the chance that dust may be trapped in its orbit. Suddenly, this is not just another discovery. It is a convergence of firsts. And that brings us to the deepest layer of the story. The universe did not change when Webb observed TWA7b. We changed. Our reach changed. Our evidence changed. Our standard for what can be seen changed. There's a quiet difference between saying the cosmos is full of hidden worlds and saying we are now building the tools that can draw those hidden worlds out of the dark. The first is a belief supported by science. The second is a turning point in civilization's powers. We are living inside that turning point. People centuries ago looked at the stars and saw mystery. We look at the same sky and still see mystery. But now we also see workflow, instruments, papers, image processing, probabilities, and mission data. Some people think that makes the universe feel less magical. I think it does the opposite. Because now the magic has a mechanism. Now wonder has engineering behind it. Now awe comes with evidence. And that makes it stronger, not weaker. So when you hear the title, James Webb just imaged another world, do not reduce it to clickbait too quickly. Under the drama, there is something real. Scientists found compelling evidence for a Saturn mass candidate planet called TWA7b, around a star 111 light years away. They used Webb's MIRI coronagraph and careful image processing to reveal a faint infrared source in a gap within a 3-ring debris disk. The object's properties fit the picture of a young world shaping the structure around it. If future work confirms it, this will stand as Webb's first direct image discovery of a planet, and the lightest exoplanet ever seen this way. That is extraordinary, not because it gives us all the answers, but because it proves we are learning how to ask the universe harder questions and actually get something back. So if this story gave you that chill, leave a like so more people find it, subscribe if you want the next chapter the moment it drops, and share it with somebody who still thinks humanity has already seen the best parts of reality. Because we have not. We are still at the beginning. A faint point near TWA7 may not look like much at first glance. No oceans, no clouds, no dramatic horizon, just a difficult signal pulled from the glare around a young star. But sometimes, history does not arrive as a fireworks show. Sometimes it arrives as a barely visible dot that forces human beings to admit they can now do something they could not do before. And those moments are dangerous in the best way. They expand the future. They make bigger dreams feel reasonable. They turn distant goals into active projects. They tell the next generation of scientists, engineers, and curious kids that the wall has cracked. And once a wall cracks, people start planning what comes through it. That is why this story matters. Not because TWA7b is the perfect world, not because the image is flashy, not because every mystery is solved. It matters because another barrier between humanity and the universe just got thinner. We used to wonder whether other worlds were out there. Then we learned they were. Now, step by step, photon by photon, we are beginning to see them. And when a species starts seeing new worlds, truly seeing them, it does not stay the same for long.